Good evening everyone, I am Shivani Dhok and I welcome you all for the week 12 tutorial of this course, Digital Signal Processing and its Application. So like every week, we'll have first the recap of week 12 content, a very quick recap, and followed by the questions which are related to the content of week 12. So this week 12 content was majorly dependent on discretization of frequency domain access. So we had this omega, which is angular frequency. We had this omega and we discretized it into n discrete points. And this discretization led to generation of carbon copies of the original signal. And the resultant signal is just addition of all those carbon copies along with the original signal. Then we said that due to generation of these carbon copies and superposition of them, there is a possibility of having aliasing. And that aliasing won't happen if the length of signal is less than n, which is the number of discrete points we are having in the discrete frequency axis. Now we wanted to exploit the convolution property of Fourier transform or DTFT, and we want to see what happens equivalently in after doing DFT, it is discrete Fourier transform. So we observe that instead of linear convolution, we get a circular convolution. Then we looked at the discrete Fourier transform DFT. So for discrete Fourier transform, if I have x of n as the signal, then its DFT will be x of k and its IDFT will be opposite thing. And okay, so this thing here x of k is DFT, and to be specific, n point DFT, which means that this k will be running from 0, 1 till n minus 1, and similarly this n will also be running from 0, 1 till n minus 1. So if this signal x of n is having a length greater than n, then we'll have to discard some samples, and if it is having a length of less than n, then we'll have to append some zeros. And similarly, we'll have the inverse DFT corresponding to that. So this was all the things that were covered in week 12. If you have any questions, then let me know. Otherwise, I'll just move on to the questions that I have planned.
Hello, madam.
Yes.
Madam, how can we separate this DTFT from DFT, madam?
Okay, so DTFT, if you observe carefully, this DTFT is x of omega, and this omega is ranging from minus pi to pi, and this is a continuous variable.
Okay.
Now this DFT is x of omega evaluated at omega equal to 2 pi k by n, and this k varies from 0 to n minus 1, which will give me x of k, and this thing is discrete. Like this k is a discrete thing. So basically, if I discretize this x of omega in the independent axis into n points, I'll get a DFT. Does this answer your question?
Yes, ma'am. Thank you.
Yeah. Okay. So let me just quickly move on to the very first question. So let's start with a very simple question that I have to cover today. So the question is, we just need to figure out the DFT of this given sequence, and let's say that this starts from n equal to 0. So this point here, that is 1, is at n equal to 0. So x of 0 is 1. So formula for DFT is x of k is equal to, and let's say we find out 4-point DFT. it will be summation n equal to 0 to n minus 1. So here n is 4. So n minus 1, 4 minus 1, 3 x of n into e power minus j 2 pi k n by capital N, which is 4. This is equal to summation n equal to 0 to 3 x of n into e power minus j pi by 2 kn. Okay, I can expand this and write it as x of 0 plus x of 1 into e power minus j pi by 2k plus x of 2 into e power minus j pi k plus x of 3 into e power minus j pi by 2 into 3k. So this I can also write as x of 0 plus x of 1 into e power minus j pi by 2k plus this quantity here will be, this thing here will be minus 1 to the power k. So minus 1 to the power k into x of 2 plus x of 3 into e power minus j 3 pi by 2 k. So now let us find out x of 0. So x of 0 will be, or let us simplify this further. So x of 0 was 1 plus x of 1 is 2 then minus 1 to the power k, x of 2 is 3 plus x of 3 is 4 okay. So now let us find out each of these values one by one. So this is my x of k, general expression. So x of 0 will be 1 plus 2 into e power 0, which will be 1, plus 3 into minus 1 to the power 0, plus 4 into e power 0. This comes out to be equal to 1 plus 2, 3, 10. Then I can find out x of 1. Is equal to 1 plus 2 into e power minus j pi by 2 minus 3 plus 4 into e power minus j 3 pi by 2. This comes out to be equal to 1 minus 2j minus 3 plus 4j, which is equal to 1, sorry, minus 2 plus 2j. Then we have x of 2, which is equal to 1 plus 2 into e power minus j pi by 2 into 2, which is equal to 2 pi by which is equal to pi plus minus 1 to the power 2, which is 1, plus 3 plus 4 into e power minus j 3 pi, which is equal to 1 minus 2 plus 3 minus 4. And if I solve this, this comes out to be equal to minus 2. Then at the end we have x of 3. This comes out to be equal to 1 plus 2 into e power minus j 3 pi by 2 minus 1 to the power 3 is minus, so minus 3 plus 4 into e power minus j 9 pi by 2. This is equal to 1 plus 2j minus 3 minus 4j, and this is equal to minus 2 minus 2j. So this thing here is x of 0, this thing is x of 1, this is x of 2 and this is x of 3. So the sequence x of k as a sequence, if I write it, then it is 10 at 0. Then I have minus 2 plus 2j. Then I have minus 2 and minus 2 minus 2j. So this thing here is DFT or 4-point DFT of x of n. Simple question. Any queries?
No, madam.
Any queries in this particular question?
No, madam. No questions.
Okay, thanks. So let me move on to the next question. So the question says that consider a train of unit impulses given by Pn equal to this quantity. So this thing here, this signal here given is known as the train of impulses where n, capital N is greater than 1 is the period, and we need to find the nature of its DTFT. So there are four options. So it is a DC waveform, a single impulse, a train of impulses with period 2 pi, and a train of impulses with period 2 pi by n. So let us try to find out the DTFT of this particular thing. Okay, so now just note that this is a periodic signal. So we can't use the formula of DTFT directly. So what we do is first we find out DTFS, that is discrete time Fourier series coefficients, and let's say these are indexed by CK, and then we find out CTFT, which is given by P of omega is equal to 2 pi into summation k running from minus infinity to infinity Ck into del of omega minus the period k times omega naught. Okay, so this is how we find this out. And here omega naught will be equal to 2 pi by, hello, okay, omega naught will be equal to 2 pi by n. Okay, so this is a standard way of doing this thing for a periodic signal. It will include some impulses. So now let us first figure out how these CKs look at. So we are given that this train of impulse P of n is summation k running from minus infinity to infinity delta n minus kn, which means that from minus n by 2 to n by 2, let's assume that n is an even integer. If it is not, we can adjust the upper and lower limit of these things appropriately. So what we can do is, for Ck or finding discrete Fourier series coefficients, we just look at one period. So Ck is given as 1 by n summation over a period n P of n into e power minus j k omega naught n. So let us take the first interval which will lie somewhere from n equal to minus n by 2 to n by 2. If it is not the case, then you can just take a seal here which will take the next higher digit of it. Wrong place. Like this. And in this from negative half to positive half, this delta n minus kn, here k will be equal to 0 into e power minus j k omega naught n. Now I'll use the shifting property of unit impulse, so this will be equal to delta n into e power minus j omega naught k into 0, which is equal to delta n. So this will be equal to something like this. Now I'm evaluating sum of an impulse from minus n by 2 to n by 2, and there will be only one impulse of value 1, and rest everything will be equal to 0. So this summation will give me simply 1 by n. Okay, so 1 by n into this summation, the summation will be equal to 1. This thing here will be equal to 1, and therefore this entire thing will give me as n. So now I have ck's, and I can substitute these ck's in this equation. So therefore P of omega will be equal to 2 pi into summation k running from minus infinity to infinity ck into delta omega minus omega naught k. This comes out to be equal to 2 pi into summation k running from minus infinity to infinity, ck's are 1 by n into delta omega minus k times omega naught is 2 pi by n. So therefore this is 2 pi by n into summation n equal to minus infinity to infinity delta omega minus k times 2 pi by n. Now observe carefully, this part here is a train of impulse with period 2 pi by n, and this train of impulse is in omega axis or frequency domain. And this thing here is simply a constant. So it is not depending on omega, and therefore it is just scaling each and every impulse. So this thing is 2 pi by n here, and it is a constant. It is scaling each and every axis by the same constant. Therefore the train of impulse nature remains as it is. So together, looking at this P of omega or dtft of this particular quantity here, that is train of impulse, we can say that we are getting a train of impulses, and the period of this train of impulse is equal to 2 pi by n. Therefore the option that is correct is this one. Any questions in this particular part? Okay, if there are no questions, then let me just move on to the next question. So the third question says that, yeah, I have seen the question in the chat. It is related to the assignment. I'll discuss this at the end of today's session. And hopefully that something related might be there in this particular question, might be helpful. So just wait till the end of today's session. Okay, so consider the statement given below. So x tilde omega is n by 2 pi x of omega into p of omega, and it gives us x tilde of n, which is equal to n by 2 pi into convolution of x of n into p of n, where x and p are as defined in the previous question. So p of n is defined in the previous question. There was no x of n. So x of n, we had some x of n. This has a DTFT as x of omega. P of n, we figured it out. This had a DTFT as p of omega, which we had obtained as 1 by n summation k running from minus infinity to infinity. Delta omega minus k times 2 pi by n, and this p of n was equal to summation k running from minus infinity to infinity delta n minus kn, which is train of impulse. Okay, yeah, this is what we are having. This is given to us in the first question. Now they say that we assert that the given statement can be used to demonstrate the occurrence of aliasing. Is this assertion true or false? So aliasing in particularly in time domain. So I need to be very specific in time domain. Yeah. So does this statement tells us something regarding that? So now just look at this x tilde n which we are having. X tilde n is n upon 2 pi x of n convolved with p of n, which is equal to n upon 2 pi x of n convolved with the train of impulse, that is k running from minus infinity to infinity delta n minus k times n, which is equal to n upon 2 pi to summation k running from minus infinity to infinity. I can apply the distributive property for convolution. X of n convolved with delta n minus k n, and this will give me n upon 2 pi summation k running from minus infinity to infinity. Any signal that we convolve with an impulse located at some location, then this convolution will give me the signal shifted by this particular location. So then we'll have this as x of n minus k. So if we observe nicely this particular term here, this is a constant. This part is a constant, so this has nothing to do with whatever is asserted. So this thing here is superposition of shifted versions of xn, and it clearly says that if they show or if they overlap, we'll have aliasing. If no overlap, no aliasing. So we started from whatever. So whatever question we are having here, or whatever assertion is given to us, just based on that information, we are able to come down to a statement where we can somehow claim whether aliasing is happening or not, and therefore this assumption or this thing assertion is true. Any questions here? Okay, so if there are no questions, then let me just go to the next question. So it says that assume for a moment that xt is a continuous time real and non-negative signal, and with a non-negative Fourier transform, that is x of omega is greater than 0. So it says that x of t has a continuous time Fourier transform x of omega, and this is greater than 0 for all omega. Now this signal xt is sampled at t equal to nts, where ts is the sampling duration. If xn represents this sequence of samples, the following statements may be true. This is a multiple correct question, and one or more of these are correct. So one relation is between this term here, and another relation is between this term here. So this term and this term we need to relate somehow, and then there are two different statements which we need to take care of. Okay, so let's start with this. So what we'll do is we'll define some notations first. So let x dtft of small omega. So let small omega be the discrete time angular frequency, and capital omega be the angular frequency corresponding to the continuous time signals. So this we are having, this is equal to, or this denotes the dtft of xn. This xn we had obtained with sampling frequency, which depends on 1 by ts. Then let x tilde of omega be continuous time Fourier transform, or let's say let us first look at the sampling that we are having. So sampling will get some x tilde t. We are looking at ideal sampling, so that will be xt multiplied by pt, where p of t is train of impulse, which is given as t running, k running from minus infinity to infinity, delta t minus kts, and therefore this will give me some x tilde t. Now x tilde of omega, let this be ctft, or continuous time Fourier transform of x tilde t. Therefore x tilde omega is given by x of omega convolved with p of omega and scaled by a factor of 1 over 2 pi. This is the property of time multiplication, which gives us convolution in frequency domain. Okay, so now again, let's say we have this p of t structure given to us and we need to figure out this p of omega. Okay, so this p of omega is equal to 2 pi into summation k running from minus infinity to infinity ak into delta omega minus k times omega s, where omega s is 2 pi by ts, which is the angular frequency or angular sampling frequency for this particular sampling thing. So this signal here is periodic with period ts, and therefore this is the fundamental frequency of this particular signal. That's why we are having an omega s coming into picture here. So now we'll first find out. So again, this is a periodic signal but in continuous time. So we'll first have to find out the Fourier series coefficients, which are AKs. So here AKs are continuous time Fourier series coefficients of PT, and then we'll substitute those in this equation to find the P of omega. So therefore this AK is given as 1 over Ts integral over a period, that is Ts by 2 to Ts by 2 into P of t into e power minus j k omega s t dt. This is equal to 1 by Ts into integral minus Ts by 2 to Ts by 2. P of t in this duration will be simply one impulse into e power minus j k omega s t dt. Again, we'll use the shifting property of impulse, so this will be equal to delta t into e power minus j k omega s 0, which is equal to delta t. And integrating delta t from a minus limit to a plus limit, so this integral in totality will give me a value of 1. So therefore this simply comes out to be 1 by ts. Now I'll substitute this ak in this equation of p of omega. So I'll have p of omega therefore p of omega is equal to 2 pi into summation k running from minus infinity to infinity into 1 by ts into delta omega minus k times omega s. So this comes out to be equal to 2 pi by ts into summation k running from minus infinity to infinity delta omega minus k times omega s. Now I'll substitute this p of omega in this equation. So therefore x tilde omega, which is equal to 1 upon 2 pi into x of omega convolved with p of omega, this comes out to be equal to 1 upon 2 pi x of omega convolved with 2 pi by ts into summation k running from minus infinity to infinity delta omega minus k times omega s. This gets cancelled. This is a constant. I can take it outside. 1 by ts is a constant. I can take it outside. And again, I can apply the distributive property of convolution. So this will be x of omega convolved with delta omega minus k times omega s, and I'll add this up for all the value of k is in integer. So this comes out to be equal to 1 by ts into summation. Let me just add a new page. Too much crowded here. Yeah. So therefore x tilde omega is equal to 1 by Ts into summation k running from minus infinity to infinity x of omega minus k times omega s. So this is the first equation that I am having. Okay, so now this is a CTFT, that is continuous time Fourier transform. Another relation that we have is this angular frequency omega is given as 2 pi f by fs, where f is a Hertz frequency and fs is the sampling frequency. So here fs is 1 by Ts and f is whatever we are having here. So f is the f is the Hertz frequency and omega is 2 pi f. So I can write this as omega upon 1 by Ts, which is equal to Ts into omega. Okay, so this is what we are having here. Another way of writing this is I can multiply this thing. So this is simply omega and I can multiply this by 2 pi. So that will give me 2 pi omega by omega s. Okay. So now I want to somehow figure out the relation between this x tilde of omega. So this is a sample to signals CTFT. So this should be related to the DTFT of this quantity here. Okay, somehow this should be related to that quantity here. Okay, so that we'll figure out now after some time. So now we are here. So just keep this relation in mind. Let me number it as equation 1. So omega is related like this. So now let me just take this equation here. Yeah, I'm having this thing here. Now I can square both the sides. Okay, now another thing that is given to us is this x of omega is greater than 0 for all omega. And when this thing is happening, then square of sum will be greater than or equal to sum of squares. So this is equal to 1 by Ts square into summation k running from minus infinity to infinity into x of omega minus k times omega s square. This is true. Okay. So this we are having here. So I can take this 1 by Ts square on the other side. So I'll have Ts square into, now since these are positive quantities, I can just simply do this also. Is equal is greater than or equal to summation k running from minus infinity to infinity magnitude of x of omega minus k times omega s squared. So this relation we are having. Okay, now what we'll do, we'll integrate on both sides over a unique range of omega for this particular thing here. Okay, so what we will do is we'll integrate it. So this ts square into integral from minus omega s by 2 to omega s by 2. We'll integrate this over unique range of omega. Okay, so this I'll have this will be greater than or equal to integral from minus omega s by 2 to omega s by 2 summation over k magnitude of x of omega minus k times omega s square d omega. Okay, then what I can do is this is over a unique range, so I can take any unique range, and by doing that I can just change this from limits like this, and since I can take any unique range of this particular quantity, I can write this as something like this. And since I am integrating all of these things from some range, and this k runs from minus infinity to infinity, and I'm taking all these particular shifted versions, I can simply write this as integral from minus infinity to infinity magnitude of x of omega square d omega. Now I can multiply both the sides by 2 pi. So what I'm having right now is 1 upon 2 pi ts square into integral minus omega s by 2 to omega s by 2 into it's greater than or equal to 1 upon 2 pi integral minus infinity to infinity magnitude of x of omega square d omega, and this thing here is equal to integral minus infinity to infinity magnitude of x of t square dt by Parseval's theorem. Now focus on this particular part. Okay, now we'll look at this particular part here. So in this equation, what we will do is we will substitute the relation for omega and capital Omega which we had obtained earlier. We have this thing here. Now we'll replace this capital Omega as small omega by ts. So we'll replace or substitute omega as omega by ts. So d omega will be equal to d small omega by ts, and yeah. So now this capital Omega varies from my omega s by 2 to omega s by 2, which is equal to minus 2 pi by ts into 2 to 2 pi by 2 ts, that is equal to minus pi by ts to pi by ts. So this small omega, which is equal to omega into ts, capital Omega into ts, will vary from minus pi to pi. So this integral here will now be equal to this thing, 1 upon 2 pi into ts square as it is. This will be minus pi to pi magnitude of x tilde of omega, which is omega, small omega ts square, sorry, not into pi ts d omega by ts. This ts and this ts gets cancelled, so 1 upon 2 pi into ts into integral minus pi to pi magnitude of x tilde omega by ts square d omega. So this thing here is equal to x of omega, which is equal to dtft of xn. So in sampled version, we are just substituting the sampling frequency and normalizing it. So that will simply give me this x tilde of evaluated at capital omega equal to omega by ts is nothing but x of omega. So therefore, now what I have is, I'll take this ts outside, then I'll have is 1 upon 2 pi integral minus pi to pi magnitude of x of omega square d omega. And this thing here will be equal to summation n running from minus infinity to infinity magnitude of x of n square. Again, this will come by Parseval's theorem. So therefore, this thing here is equal to ts into summation n running from minus infinity to infinity magnitude of xn square. And this thing we had obtained as greater than integral minus infinity to infinity minus infinity to infinity magnitude of x of t square dt. So this thing is greater than or equal to integral minus infinity to infinity magnitude of x of t square dt. So this is the first relation that we have obtained. So yeah, I had written this correct earlier. So this thing is greater than this thing. So this is the first option that is correct. Now next thing is, when will this equality hold? So this inequality came when we were looking at this particular quantity. Okay, so this thing x tilde of omega will be equal to this quantity when there won't be these things coming into picture, and this k running from minus infinity to infinity, these things coming into picture. And this will happen when we'll have band limited signal. So the equality will hold when I'll have a band limited signal. Why? Because at the end we are evaluating this integral over a unique range. So when this will be like k equal to 0, at that time these two integrals will become exactly same, and that's why the equality will hold if the signal is band limited. And one more condition is that my sampling frequency should be greater than the Nyquist rate, that is twice the maximum frequency. So option A and option C are correct. Is this clear? If you have any questions, then let me know. Otherwise, I'll move on to the next question. Okay, if there are no questions, then let me move on to the next question. So here is a simple common data for the next few questions. So we are given an endpoint sequence xn, and it has an endpoint DFT as capital X of k, which is defined something like this. So this is a standard definition, but one thing you should notice, that this X of n is a endpoint sequence. This is an important thing, and it's endpoint DFT. So this thing here is its endpoint DFT. So that we need to take care of in the coming questions. So let's start with the fifth question. So it says that let 4n point sequence, so consider a 4n point sequence yn, and this y of n is defined as yn equal to xn for all n from 0 to n minus 1 and 0 otherwise. So it says that this y of n is a sequence like x of 0, this starts at 0, x of 1, and so on till x of n minus 1. Then we have 0, this is at location n, and so on 0, and this will be at 4n minus 1. So this is how the sequence y of n look like, and therefore now this y of n has a 4n point DFT as y of k. So this has 4n point DFT, which is given as y of k, and it is said that x of k is y of 4 times k, and we need to figure out whether this is true or not. Okay, so now let us first start with the definition of y of k. So it is a 4n point DFT, so this y of k is given by summation n running from 0 to 4n minus 1 y of n into e power minus j 2 pi k small n upon 4n. This comes out to be equal to summation n running from 0 to 4n minus 1 into y of n into e power minus j pi k n by 2n. Now for n equal to 0 to n minus 1, y of n is equal to x of n, and otherwise it is 0. So I can split this summation into two parts. So this y of k is equal to summation n running from 0 to n minus 1. In that part, y of n is equal to x of n into e power minus j pi k n by 2n plus summation n running from capital N to 4n minus 1. In this location or in these particular values, it is 0 into e power minus j pi k n by 2n. So this entire part goes to 0. So now we have summation n equal to 0. So this y of k is equal to summation n equal to 0 to n minus 1 into xn into e power minus j pi k n by 2n. Now if you observe in the question, what is said is this xk is equal to y of 4k. Now what we have is, we have y of k here. So now let us find out y of 4k. So this comes out to be equal to summation. We are just changing k, or we are just replacing k by 4k. So this summation limit will remain as it is, n running from 0 to n minus 1. This x of n will also be remain as it is. It's not a function of k, into e power minus j pi. This kn is replaced by 4k into n by 2n. So this gets cancelled like this, and now what we are having is summation n running from 0 to n minus 1 x of n into e power minus j 2 pi k n by n. Now if you observe the given date information to us. So x of k is n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n, and this is what we are obtaining here. So this thing here is equal to x of k. So therefore y of 4k is equal to x of k. So therefore the given statement to us is true. Is it clear? Any questions? Okay. Yes, any questions? Okay, fine. If there are no questions, then let me move on to the sixth question. So it says that now consider another 4 endpoint sequence. Again, I have a 4 endpoint sequence z of n defined as z of n is equal to xn for n ranging from 0 to n minus 1, and z of n is equal to x of n minus 2n for n ranging from 2n to 3n minus 1 and 0 otherwise. Okay, now zk is a 4 endpoint DFT of Zn, then which of the following options are true? So what is given to us? We have Zn. So this is a 4-point sequence, sorry, 4 endpoint sequence. Okay, so now this Zn is equal to x of n for all n ranging from 0, 1 and so on till n minus 1, and this is equal to x of 2n minus n, sorry, n minus 2n for all n ranging from, no, it's not a multiple answer type question. Whenever it's a multiple answer type question, I'll mention that it is multi-correct. Or at least the question will have that which of the following statements are true. I'll generally mention like this. If I miss, it will be very clear. Yeah, so x of n minus 2n, this is what I'm having here for n ranging from 2n to n plus 1 and so on till 3n minus 1. It is 0 otherwise. So let us first construct this sequence. So this z of n is equal to x of 0 at 0, x of 1 and so on till x of n minus 1. So this location is n minus 1. Then at x of n, it is, so this particular thing starts from n equal to 2n. So for x of n, or sorry, z of capital N, it's a 0. So this is the location n, and the 0 continues till the location 2n minus 1. Then at location 2n minus 1, I'll substitute it as x of n minus 2n. So x of 2n minus 2n will be 0. So I'll have x of 0. This is at n equal to 2n. Then it will be x of 1 and so on till x of n minus 1. And this location will be 3n minus 1. And after that, that is from n equal to 3n, it will be 0 and so on like this. So this is 3n. So this is how our z of n look like. Okay, so now I can split this into two sequences, something like this. So the z of n I can write as x of 0, x of 1, and so on till x of n minus 1, 0. This is at n, and so on 0. This is at 4n minus 1. So this location here is 4n minus 1. So this is the first sequence, and plus I have another sequence. So I have already added this sequence. So now this part should go to 0, and from n equal to 2n to 3n minus 1, it should be a non-zero quantity. So I can write this as 0. This is at 0. This is at 0, and so on 0. This is at 2n minus 1. Then I'll have x of 0, and so on till x of n minus 1. This is at 2n. This is at 3n minus 1. Then I'll have 0 from 3n, and so on 0. This is at 4n minus 1. So now if you add these two sequences, then I'll get this z of n sequence. So why am I doing this kind of thing? So these options which are given below are in terms of zk's and yk's. So somehow I have to introduce y of n into picture. So now if you observe this particular sequence here, this particular sequence is equal to y of n. See, this is my y of n. It is initially x of n and 0 otherwise. So this sequence, the first sequence, this part is x of n, and for remaining other 3n values it is 0. So this particular sequence here, this is y of n. Now if I shift this y of n by 2n units, that is, if I shift this y of n sequence rightwards by 2n units, that will give me this particular sequence. So therefore this sequence here, see, this is y of n, this part is y of n. Now I'm shifting this y of n. It starts from 2n. It starts from 2n. All the values of uh, n equal to 0 to 2n minus 1 are 0. So we are just shifting it by 2n units. So therefore this particular quantity here is y of n minus 2n. So therefore this z of n comes out to be equal to y of n plus y of n minus 2n. Okay, so this is what we are having now. Now let us take 4-point DFT. So then I'll have z of k is equal to y of k, plus I'll introduce the time shift property of this. So it will be e power minus j 2 pi k into 2n by 4n multiplied by y of k. So this is equal to y of k inside the bracket 1 plus this gets cancelled. So it will be minus 1 to the power k. So this is what I'm having here. Now nowhere these options zk minus y of k equal to y of k or zk minus y of k equal to minus y of k come into picture. So now let us look at the third option that we are having. So let's substitute, let us find out z of 4k. So z of 4k will be equal to y of 4k into 1 plus minus 1 to the power 4, which is equal to 2 times y of 4k. Now this y of 4k is equal to x of k from the last question. Y of 4k is equal to x of k from the last question. So we have y of 4k is equal to x of k from the last question or the previous question. Therefore, z of 4k is equal to x of k, or rather 2 times x of k. And this is the third option that we are having. So z of 4k is equal to 2 times of x of k. And this is the answer. Is it clear? Any questions in this particular part? Okay. If there are no questions, then let me move on to the next question. Yeah. So the next question says that let xn be a 4-point sequence and let vector x be equal to x of 0, x of 1, x4 and x3, capital X's. And these indicate the vector that stacks all the 4 values of 4-point DFT. And let x be a vector, small x be a vector where it is given as something like this. So I have this x vector which I'll denote by x underlined x, just because I can't show bold letters here. So this is equal to x of 0, x of 1, x of 2 and x of 3 transpose, and small x vector is equal to x of 0, x of 1, x of 2 and x of 3 transpose, and it is given that this x is equal to m into x. So this is basically vectorized version of DFT. Okay, so now let us try to construct this particular matrix M. So this M is a matrix, n cross n matrix. So now we have, just look at x of k now for some value of k. So this is equal to summation n running from 0 to capital N minus 1. N is 4, so 3 into x of n into e power minus j 2 pi k n by 4, that is equal to summation n running from 0 to 3 x of n into e power minus j pi k n by 2. And I can write this as x of 0 plus x of 1 into e power minus j pi k by 2 plus x of 2 into e power minus j pi k plus x of 3 into e power minus j 3 pi by 2 k. Okay, so now this x of 0 is for specific values of k's. Will have x of 0 plus x of 1 plus x of 2 plus x of 3. Then for x of 1 we will have x of 0 plus e power minus j pi by 2, which is equal to minus j x of 1 plus e power minus j pi, which is minus into x of 2 plus x of 3 into e power minus j pi by 2, j3 pi by 2. So this will be plus j into x of 3. Then I have x of 2 as x of 0 as it is, Then I'll have x of 1 into e power minus j pi, so minus x of 1. Then I'll have plus x of 2 into e power minus j 2 pi, so plus x of 3 and minus x of
X of 2 met.
2,
It
sorry.
is X of
Yeah,
2 met.
thank you. And then I have capital X of 3. This will be equal to x of 0 plus j times x of 1 minus x of 2 minus j times x of 3. So these are the equations that I'm having, and now I have to construct that particular structure, that is x equal to mx, capital X equal to mx. So we have this capital X as like this. Then I have a matrix coming here, and then I'll have this x vector, that is x of 0, x of 1, x of 2 and x of 3. So these are basically 4 simultaneous equations in 4 variables. So this x of 0 is 1 into x of 0, 1 into x of 1, 1 into x of 2, 1 into x of 3, and all added. So this will be 1, 1, 1, 1. Then I have for x, so capital X of 1, x of 0 as it is, minus j times x of 1 minus x of 2 plus j times x of 3. And then I have 1 into minus 1, uh, x of 0 minus x of 1 plus x of 2 and minus x of 3. Then for x of 3 I have x of 0, j times x of 1 minus x of 2 minus j times x of 3. So therefore this thing here is x, this thing here is small x vector, and therefore this thing here is m. So therefore the relation that I'm having here is this x is equal to m into x, and I need to find out the determinant of this quantity. So now this is a 4 cross 4 vector, 4 cross 4 matrix, and finding determinant of this is cumbersome. If the dimension of this m increases further, it will be much more cumbersome. So now what we will do, we'll look at some property of this DFT and see what happens, or what do we understand by looking at these things, or somehow can we exploit the properties of DFT. So for that, what we will do is, we have that we have this case that x of n has a DFT of x of k, right? Now let us figure out what happens if we find out, if we have the signal as x of n and we find out its endpoint DFT. What do we get? So let's say this is equal to x tilde of k. So therefore this x tilde of k is equal to, so this thing is equal to summation n running from 0 to capital N minus 1, capital X of n into e power minus j 2 pi kn by n. Then what I can do is, I can write this as summation n running from 0 to n minus 1 x of n into e power minus, so I'll do this, e power j 2 pi into minus k n by n. Now this x of k's are also periodic, so this x of this quantity here, is equivalent to n naught to e power j 2 by n minus kn by n. So this is just flipped version of this signal in that particular k running from 0 to n minus 1 region. This is just a flipped version. So this thing here is simply x of n minus n, small x of n minus n, but multiplied by n. So if you observe carefully, if I multiply and divide this by n, then this particular part resembles the DFT of inverse DFT of capital X of n evaluated at n minus k. So just because we are having a periodic thing coming into picture, or rather replicas coming into picture, instead of minus k, I'm just replacing it by n minus k, so that I have the range of this, sorry, not minus n, this small k, yeah, range of this k from minus 1 to from 0 to n minus 1. So what do we observe is, I had this x of n. If I find its DFT, I get x of k. Then if I find its DFT again, n point DFT again, I get n times x of n minus capital N minus n, or let's say some other thing. L. Then if I find its DFT again, I will get, this is a flipped version, so I'll get n times x of n minus m. And now again, when I find its n point DFT, now this is the signal that I'm having, so I'll have a multiplication by n there. Now this is the inverse DFT of the signal, whatever we were having. Now this thing, when I find its inverse DFT, I'll get an x, but now I'll have this shifted by, so I'll have n minus this quantity, that is n minus p, let's say p. So this gets cancelled, and I'll get, and yeah, there will be a multiplication by n, so I'll have n square x of p. Okay, so what is happening is, first time I am having multiplication by m here. So this is the vector x that I am having, so I'll multiply it by m. So this quantity here is mx. Then I'm again multiplying it by m. So this quantity here is m square x. Then again I am multiplying it by m here. So I am getting m cube x, and then I am multiplying it here again by m. So this will give me m to the power 4x. And now if you observe, we had started with x of n, we are getting x of n, but now scaled by a quantity of n square. So this vector, when we stack, this will be equal to n square times x. So therefore this quantity here is equal to n square times x. So therefore what we have is m to the power 4x is equal to n square x. And therefore I can write it as m to the power 4 minus n square into x is equal to 0. Now note that this resembles that eigenvalue, eigenvector kind of equation, but this is not an eigenvector of this m to the power 4. This is any arbitrary vector that we are having. So this is not an eigenvalue or of kind of expression coming into picture. Therefore this equation should be satisfied for any arbitrary, so yeah, there will be an identity matrix here, yeah. So any arbitrary value of equation, value of vector x, this should satisfy. So this x can be non-zero, this x may not be an eigenvector of m to the power 4, and if that has to be true, then this m to the power 4 minus n square I should be all zero matrix. And therefore m to the power 4 should be equal to n square into I. And if I find determinant of m to the power 4, that will be equal to determinant of n square I. So therefore, this will be equal to determinant of m to the power 4 is equal to n to the power 2n. So this identity matrix is of n cross n dimensions into determinant of I, which is equal to n to the power 2n. Now if I take absolute values on both sides, so I'll have, or rather determinant of m will be equal to n to the power 2n by 4, which is n to the power n by 2. So therefore absolute value of determinant of m is equal to absolute value of n to the power n by 2, which is equal to, so here in our question n was equal to 4 to the power 4 by 2, which is equal to determinant absolute value of 4 to the power 2, which is equal to 16. So therefore magnitude of determinant of m is equal to 16. Yeah, so this is what we are having here, and therefore the final answer is this one. Yeah, so similar question was there in chat. So one question appears in assignment of finding trace of m in an equation y equal to mx, where y and h are column matrices. Can you throw some light, as unless h transfer to left side it's impossible to find the trace, or can we leave it by finding trace of y and by trace of h, making y and h as square matrices and indicate finding trace? As far as I understand, this y equal to mh should be some kind of relation as there in this particular equation. So you can find a generalized relation of m, or generalized thing of structure of m, and then figure out the trace of m. I think that should be helpful. Then this y and h are column vectors, so writing trace of y and trace of h doesn't make sense. And trace of a into b is not equal to trace of a into trace of b. That kind of thing doesn't happen. So therefore trace of m will never be equal to trace of y upon trace of h. There are some bounds there, so that kind of approach won't make sense. So if m corresponds to this DFT IDFT kind of relation, then you can figure out some generalized relation the same way we did here. So here we did it for n equal to 4, but then you will have to do it for, I don't know if it is for any arbitrary value of n or for n equal to 4. If it is this kind of thing coming into picture, you can find a generalized relation and then find out the trace of n. That will, I think that is what being asked. I don't know the exact question, but yeah, the approach which you are mentioning doesn't seem correct, because you can't do such kind of operation. Trace is not, you can't have trace of a into b is equal to trace of a into trace of b. I hope that is clear. Does it make sense to you, sir? Is it clearer now? Okay, I assume that it's clear. If you have any questions, then let me know. Otherwise, I'll move on to the next question. Yeah, so this DFT matrices are, when you appropriately scale them, are what do we call, unitary matrices. So there are many ways in handling unitary matrices. So you can also look at the properties of them, so that those are helpful. Okay, if there are no questions, then let me move on to the next question. So for question 8 to 10, we are having this common data. So it says that I have a 4-point signal x of n, which is given by a sequence as 1 2 2 3. So this is at n equal to 0, like x of 0 is 1. Then note that this okay, that is only given, and for other values of n, your x of n is equal to 0. So this is the x of n that we are having. Now let us go to the question that is given to us. So it says that what is the 4-point circular convolution of x of n with itself. So the given x of n is equal to 1 2 2 3, and then we need to find out the circular convolution with itself. So what is x of n circularly convolved? So here n equal to 4 with itself, like this. We need to find this out, and for that we'll look at a very like easy approach. So it is a circular convolution. So what we will do, we'll arrange x of n in a circular manner, like this. Okay, and then we will arrange the other signal. Let's say I have x of n circularly convolved with h of n. So I'll arrange that h of n. So this is x of 0. This is x of 0. So I'll start from here. And since I have arranged x of n like this, in this direction, increasing direction of n, now I'll arrange the other signal in the opposite direction like this. So now here my x of n is like my h of n is equal to x of n. So now I'll arrange it like this. So 1 2 2 3. So opposite direction like this. And then what I'll do, I'll element by element multiply and add. So let's say I have this y of n as x of n circularly convolved with itself, or let's say it's y4 of n. So therefore y4 of 0 will be equal to 1 into 1 plus 2 into 3, that is 6, plus 2 into 2, that is 4, plus 2 into 3, that is 6. So this comes out to be equal to 17. Okay, now I'll have to shift it by a unit. So generally in linear convolution, I'll shift it rightwards. Okay, so the generalized formula for this quantity here is summation over k, which is from 0 to n minus 1, or 4 minus 1 here, x of n minus k into x of k. So this inner one is just x of k, and this outer one is x of n minus k here. Not capital N. N minus k, but modulo n. So n minus k modulo n. This is the formula for linear circular convolution. So now it's similar thing. So we are flipping it, and now we'll have to shift it rightwards. But now when we are shifting it rightwards, we were basically shifting it in the increasing order of k of the original signal, right? So now in this thing we are having an increasing order of k like this for the inside circle. So now this flipped version of x of k, which was like this, now I'll shift it by 1 unit this direction. So now what I'll have here is, earlier my 1 was here, so now this will go here. So I'll have 1 2 2 3. Again I'll do element by element multiplication, and that will give me y4 of 1 as 2 into 1 plus 2 into 1 plus 2 into 3, 6, plus 2 into 3, 6, and this comes out to be equal to 16. Now here we are. So my 1 now starts from here. Now for y4 at 2, I'll shift it by 1 unit more. So now my 1 will start here. Now in the anti-clockwise direction, I'll write the signal because increasing direction of k was clockwise, like this. Now again, I'll do element by element multiplication, like this. And therefore, this y4 of 2, so this is, yeah, is equal to 2 into 1 plus 3 into 3, 9, plus 2 plus 4. And again, this comes out to be equal to 17. Now this is y equal to y4 of 2. Now I'll, for y4 y4 of 3, I'll have to again shift it by 1 unit. So now I am here, this is my reference point. I'll again shift it by 1 unit like this. So now my 1 will start here, then 2, 2 and 3. Sorry, 1, 2, 2, 3, like this. So I'll again multiply it element by element like this. So now what I am left with is, so this will be equal to 1 into 3 plus 1 into 3 plus 2 into 2, 4 plus 2 into 2, 4, and this comes out to be equal to 14. So now again, so this is at n equal to 3, small n equal to 3. Now again, if I shift it like this, my 1 will be here. So that will give me 1, 2, 2 and 3, which is the original equation. So it simply says that after small n equal to 4, it will again start repeating. So it means that y of n plus k times 4 will be equal to y of n, where k belongs to the set of integers, and y of n is equal to, at 0 it was 17, then at 1 it was 16, at 2 it was 17, and at 3 it was 14. So this thing here is 4-point circular convolution of x of n. Is it clear? Any questions? Okay, we'll repeat a similar question but for a higher value of n now. So now what we will do, we'll find a 10-point circular convolution of x of n and x of n, like x of n with itself. So for that, our x of n was a 4-point sequence. So x of n was given to us as 1, 2, 2, 3. So this is a 4-point sequence. Now in order to make it 10-point, I'll append 6 zeros. Like this. Now again, this inner circle, I'll construct an inner circle. So this inner circle will correspond to x of k, and its increasing direction of k will be like this. Now in order to find circular convolution, the other signal, which is again x of n here, I'll flip it and write it. So if I flip it, the origin will be the same initially like this. So zeros, x of zeros and other signals 0th element should coincide when you're flipping it for the first time. Then I'll write the signal in the opposite direction like this, and I'll add zeros otherwise like this. And now I'll again do element by element multiplication. So this 1 will get multiplied with 1, this 2 will get multiplied with 0, 0, 0, 0, 0, 0, 3 into 0, 2 into 0, and 2 into 0. So therefore, so this is 10-point DFT, so y10 of 0. So let me just write it properly. This is y10 of n is equal to x of n, 10-point circular convolution with itself. So therefore this y10 of 0 comes out from only this part, others all are 0, so this comes out to be equal to 1. Now I'll shift it by 1 unit. So I was here initially, so I'll shift it by 1 unit, so it will be 1 2 2 3 0 0 0 0 0 0, and again I'll do element by element multiplication, so I'll have 2 into 1, so this is y10 of 1, so this will be 2 into 1 plus 2 into 1 multiplied by 0 plus 0 0 0 0 0 0 0 and 0, so this comes out to be equal to 4. Now I am at this location, this is my now new origin, that is this point. Now I'll again shift it by 1 point here, so now my 1 will start from here, so I'll have a 1 here, then 2 2 3 0 0 0 0 0 0. So I'll have 2 into 1, 2 into 2, 2 into 1, then plus 0 0 0 0 0 0 and 0. So therefore y10 of 2 is equal to 2 into 1 plus 2 into 2 4 plus 2 into 1 2, so therefore this comes out to be equal to 8. Okay, now we are here. Again I'll shift it by 1 unit, so now I'll come here like this, and rest all will be equal to 0. So now I'll have y10 of 3 as 1 into 3 plus 2 into 2 plus 2 into 2 plus 3 into 1 plus 0 0 0 0 0 0. So this comes out to be equal to 3 plus 4 plus 4 plus 3. So this comes out to be equal to 14. Then I have, now I am at this location, I'll again shift by 1 location here. So now I'll come at this point. So I'll be now at this point. So I'll have 1 2 2 3 0 0 0 0 0 0, and this thing here will be y3 of 4, sorry, y10 of 4. And this thing will now be equal to, sorry, yeah, I'll start from this point, and I'll have 2 2 3 0 0 0 0 0. 2 into 3 plus 2 into 4 plus 2 into 3 plus 0 plus 0 plus 0 0 0. This will also be 0. So this y10 of 4 will come out to be equal to 6 plus 2 into 2 4 plus 2 into 3 6. So this is equal to 16. I am at this location. Again I'll shift by 1 unit. So now I'll be at here 2 2 3, remaining all will be 0 like this. Then this is equal to 0, this is equal to 0, then 2 into 3 plus 2 into 3 plus 2 into 0 0 0 0 0 and 0. So therefore y10 of 4 will be equal to 2 into 3 6 plus 2 into 3 6, which comes out to be equal to 12. I am at this point. Again I'll shift by 1 unit here. So now I'll be here 2 2 3 0 0 0 0 0 0. 1 into 0 plus 2 into 0 plus 2 into 0 plus 3 into 3 plus 2 into 0 plus 2 into 0 plus 1 into 0 0 0 and 0. So now I have y10 of, so this is not 4, this is 5. So I have y10 of 6 now. This comes out to be equal to 3 into 3, which is equal to 9, and rest all are zeros. So now I am at this location, that is this location. I'll again shift by 1 point. So now I'll be at here. So this is 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So this is 1 into 0 plus 2 into 0 plus 2 into 0 plus 3 into 0 plus 0 plus 0, 0, 0, 0 and 0. So therefore this y10 of 7 is equal to 0. I am at this point. I'll shift here now. So now I'll come here. So it will be 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So it is 1 into 0 plus 2 into 0 plus 2 into 0 plus 3 into 0 plus 3 into 0 plus 0 plus 0 plus 0 plus 0 plus 0. So again y10 of 8 is also equal to 0, and this is the last point that we need to check at. So again I'll shift it by 1 unit in the increasing direction. I'll have 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So no overlap here, no overlap here, no overlap here. This is also 0, 0. This is also 0. This is also 0. This is also 0. This is also 0, and this is also 0. So again this y10 of 9 will be equal to 0. Now for y10 equal of 10, I'll shift it at this location. So I'll be at here 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So this is exactly equal to the structure that we had for y of 10 of 0. So therefore what we have is, y of 10 of n plus k times 10 is equal to y10 of n for all value of k belonging to integers, and this y of n we have obtained as 14814, 14814. Then we have 16, 12, 9, 0, 0, 0. And this starts from n equal to 0. So this is the 10-point DFT, 10-point circular convolution of x of n with itself. Is it clear? Any questions in finding circular convolution of any given signal?
Clear, ma'am.
Okay, yeah. So let's start with the last question that I have planned to cover today. So it says that for what is the smallest value of p for which the p-point circular convolution of x of n with x of n is equal to the linear convolution of x of n. So we have, let's say, yp of n, which is x of n circularly convolved with x of n, and this circular convolution is of order p. That is, I am finding p-point circular convolution of this signal x of n with itself. So now we know that for a linear convolution, or when we are finding, so let's say y of n is equal to x of n convolved with x of n, and this is linear convolution. And p here should be equal to length of y of n, so that when I circularly convolve these two signals, it will give me my y of n, so that there is no circular overlap. Like we have some zero is coming into picture, that's why like this. And length of y of n is simply equal to length of x of n, or the first signal, plus length of x of n, which is the second signal, minus 1. Length of x of n is 4, plus 4 minus 1, which comes out to be equal to 7. So P equal to 7 is the smallest value of or P equal to 7 is the smallest value of P, which will give me circular convolution of x of n with x of n as the linear convolution. So if you observe 1, 2, 3, 4, 5, 6, 7. So these first 7 values are simply the linear convolution values of y of n, of x of n with itself. You can check by performing a linear convolution. You will get these values. So if you append more and more zeros, the next remaining values will be 0. So first 7 values were non-zero and remaining will be 0. So these first 7 values will correspond to the linear convolution of x of n and y of n. So the smallest value of P, which will give me linear convolution equivalent to the circular convolution, is 7. Is it clear? Any questions in this part? Okay. Okay, if there are no questions, then there was some question in chat. So it is asked that another question, RHS is defined as integral from 0 to 6 pi of x square of omega d omega. Can I change the upper limit of the function as 2 pi and multiply 3 without of integral so that I can use Parseval's theorem? A more proper argument will be you use periodicity of x of omega. So this x of omega is periodic with respect to with a period 2 pi. So the 0 to 6 pi is basically three independent or three intervals of 2 pi, that is 0 to 2 pi, 2 pi to 4 pi, 4 pi to 6 pi. And then you split that in 4 parts and then you apply periodicity property of x of omega. And then you can apply Parseval's theorem. And I think overall you will get the same answer, but a more justified argument will be use of periodicity. Or in other words, you have replica of x of omega at 0, you have replica of x of omega at 2 pi, you have replica of x of uh, omega at 6 pi also. So in that way you are having three replicas of x of omega from 0 to 2 pi, 0 to 6 pi. So just check how to figure that out. That will be, yeah, but yeah, you can use a similar argument. It should give a similar answer, but still, just work out with the periodicity and replica thing coming into picture. You should get a same answer. I hope that answers your question. If you have further questions, then please let me know. This was all that I had planned to cover today. If you have no further questions, then you may leave the meeting. Thank you for attending today's session, and most probably I'll have a summary session on Monday. So if you have any queries, please post them in the
Madam,
ask. 1 second, sir. Please post the queries, whatever you have, uh, before Sunday, like by tomorrow night or Sunday morning, so that I can find the solutions to them and include them in my presentation. Yes, sir. Please ask your question.
same thing, madam. Whatever you told, no, regarding that only I want to ask.
Yeah. You will get a mail.
Madam.
Oh, huh. Just whatever queries you have, just post it before time so that I can
Before
prepare.
Monday, madam?
Before Sunday, 12 noon.
Okay.
Yeah. Okay. Thank you for attending today's session. If you have no further questions, then you're free to leave the meeting.